Thank you for attending here this afternoon, my use case. And probably you will end up being expert meteorologist in 20 minutes, and you will understand why we are needed while we have weather forecast in our phones. So first of all, I'd like to start with some background about myself. So I'm from Barcelona, I'm an industrial engineer, and I'm currently a product owner at MeteoSim. This is my third Airflow Summit, and this is myself presenting last year in San Francisco. And a fun fact about me, which is something that probably happens to many of us here, is that my family doesn't understand what I do, and I don't really know how to explain to them what I do. So let's talk about what we do at MeteoSim. Well, we provide basically environmental solutions. So we run weather and air quality forecasts in over 80 countries. And in total, we run around 600 automated numerical simulations per day. Some of the solutions that we offer are based on risk management. So we help companies plan operations or activate emergency plans based on weather forecasts. We also help companies navigate the regulatory from their local countries. Air pollution and emissions is heavily regulated, so we help them via our product understand if they are in compliance. And we also offer climatological studies, which is not just how much the temperature is going to increase in the next 50 years, it's also how much energy I will be using in 50 years due to climate change. So some of the sectors we work are, for example, insurance companies, where we help them assess risk for extreme weather conditions. So, for example, we help them price policies or decide whether they have to pay out in the event of damages. In oil and gas companies, we help them react to emergencies. So if part of an oil and gas plant explodes, what's going to happen? How should we mitigate the emergency? In mining companies, we offer them an option to plan their operations. So when it's the best time to move this material from here to there, or when is the best time to do a blast operation. In the case of wastewater, we help them track the source of smell complaints so they can mitigate that. And in public institutions, we help them with climate change reports, as well as installing pipelines for national weather services. So the basis of what we do is complex. We have to solve systems of partial differential equations, and we do that by using various numerical simulations. And here is the part where I told you before, you will become expert meteorologists. So several institutions around the world publish what it's called global models. So for example, here in the US, NOAA publishes the GFS. That's a representation of the atmosphere at any point in the world. So we can know exactly at a certain hour in the next 15 days, and at a certain point, what's going to be the temperature, the wind speed, wind direction, etc. What we do is take this information and use it in our local models. So we create weather simulation tailored to a specific location. So for example, we could simulate the area around Barcelona. So we use the global model plus some parameters that we need to find to run these simulations and obtain very high resolution models, up to 300 meters, which I believe it's around 900 feet, and 10 minutes. Once we have this 3D representation of the atmosphere in very high level is when we can then move on to generate air quality simulations. And here we use different models because it's not the same a model for when there is a chemical emergency and you need answers in 10 seconds, or when you want to assess the pollution in a city in the next 3 days. So at MeteoSim 4 years ago, we used GrantUp to manage all these simulations, so all the downloading, all the generating the weather forecast, the air quality, the insights, etc. And as you can imagine, it was unmanageable. So we migrated to Ferrari, we would say. We migrated to Airflow, which is the tool we use to orchestrate our simulation models. Let's take a look on how our DAGs work. So we have like different types of DAGs available. On the one hand, we have the DAGs that allow us downloading these global models, which are unique, obviously, for all our local simulations. We then have the actual local weather simulation, which is a DAG that basically preprocesses the data, which means cutting the global model to the region we are interested in, adding some configuration parameters, etc. We run the simulation, we process the simulation so that we obtain a bunch of files, and based on these files, we can then generate insights. Finally, we have the DAGs that allow us to run the air quality simulations, and as you can see from this PowerPoint presentation, it's the same as the local weather simulation. Now, the link between global models and our local weather simulation is based on the external task operator. We do that because we have to ensure that our customers always have the freshest possible local weather simulation. So if a certain day the global model downloading fails, we still run the simulation but by just using the previous global model. This way we ensure that we are always providing weather simulation. Instead, the link between weather simulations and air quality simulations are sometimes based on assets, and some other times they are based on having them in the same DAG. So all these simulations are complex, as you can imagine. Solving differential equations is always hard. So our processes are very power hungry. And I've prepared a slide tailored to this Airflow Summit. So let's suppose we have a cluster with 256 CPUs, 1 terabyte of memory, and probably between 500 gigabytes and 1 terabyte of disk space. And we want to run a local simulation in the Washington state, which gives us a forecast for the next 72 hours at 1 kilometer resolution. And we want to get this forecast once per day. If we, in this case, the compute time would be around 10 hours. We can, of course, reduce that by adding more CPUs. But just this cluster, knowing all the data transfer costs as well, it would cost us around $5,000 to $6,000 per month in the cloud. This is why we have our own HPC. So I'm now moving on to how we run Airflow. We have our own HPC in a data center, and this HPC is managed by Slurm. Slurm is something that probably none of you have heard of. Is basically like Kubernetes. It manages resources and allocation. So I just tell Slurm, hey, I have this simulation. It requires this many CPUs, this architecture, and this memory. And then Slurm decides in which node the simulation is going to be run. We then have a couple of virtual machines so that we have a high availability where we have Airflow installed. And we are thankful that we have this high availability because once a month, one of the machines will go down, so the other one can take over. And in these machines, we have a custom operator and a custom trigger, which I will go into it later on. And finally, we also developed an intranet, which is the place we develop all of our DAGs. So last year's presentation was about how we managed to make Airflow and Slurm to work together. I've left you the QR code if anyone is interested in that type of technology, but I'll go into it in just 2 minutes. So on our Airflow installation, on the scheduler, well, on the executor actually, we have a Slurm operator that runs. This Slurm operator, what does is store the task information in a Redis database. So this task information includes the code that needs to be run, so the kind of the parameters of the simulation, as well as the resources that the simulation needs. On our HPC, we have a daemon which receives this information and executes the Slurm command to allocate resources for that task, which is sbatch, which then returns us a job ID, which we pass to the Slurm operator. Once we have that, we defer to the Slurm trigger so that everything from this point on is async, so we use fewer resources. Then we have another daemon on our HPC cluster that basically monitors all the Slurm jobs and stores in a Redis database the status of all of those jobs. So our Slurm trigger just have to monitor that database and check for the task status. When it's okay or failed, the Slurm trigger also ends the Airflow task. Moving on, we also have that intranet I talked to you about, and we have like a very easy to use intranet for our operations people so that they don't have to actually learn Airflow. They don't have to write any Python code. And also it helps us managing changes. So if a parameter changes, something changes, it's just an SQL command that needs to be run. And we also are able to run statistics on all the tasks that we have. So for example, how many simulations use more than 128 CPUs, or how many simulations are in this area, etc. All this information is then stored in a YAML file as well, which is processed by DAG Factory. So, why did we choose Airflow in the first time? 3 years ago or 4 years ago, I don't remember exactly, when we saw that crontab was not useful for us, we had to go on the market and see what was available. And there are several orchestrators, but we chose Airflow for many things. One is that it's open source, so that's always a plus. And we know that there is a big community behind it, and very big companies that also use it. So it gives us the assurance that the project is not going away anytime soon. Also, Airflow has an intuitive web interface where we have everything there. It helps us not having to remember cumbersome Slurm commands. We have automatic retrace for failed tasks, which is something we did not have with crontab. We also have a notification system, so we don't have to invent the wheel again. And thanks for Airflow being so extensible, we can support YAML DAGs as well as integrate it with our own Slurm cluster. Moreover, Airflow gives us the power of visibility, so we can have all the run history on the web page. It's very easy to see which days certain DAG failed. We can also see real-time logs on the web page, so that we don't have to go to the cluster, find a specific file, and make sure it's the one that we have to look at it. And well, since then, we decided we would use Airflow a lot. And not only for the 4 types of workflows I showed you before, but we also use it for validation, for reporting, notifications, or even cleanup. In fact, in our instance, and just to make these numbers even bigger for you, we are a company of just 25 people, and the technical people are maybe 10. We have 600 active DAGs, which generate 2.2 million annual DAG runs, and we have a pretty high success rate of 96%. The rest is normally external HTTP APIs, which, well, if they fail, there is really nothing we can do about it. So that's my last slide, and it's what's next for us with Airflow. So Airflow is part of our core business. Airflow runs everything within MeteoSIM. So what we want to do first is to upgrade to Airflow 3.1. We are currently in 2.10, and there are several reasons why we want to do that. Well, first of all is because we are excited about the new UI. Obviously, I guess everyone is excited about that change. But also because we now have online backfills, and that was a must-have for us. So every other week, I will have one of our operations people come to me and ask me, hey, Eloi, how did we have to do a backfill? So I will have to set up access to the virtual machine where we have Airflow installed, and then remind them of the command, and that wasn't working for us anymore. So we are very excited about that feature in Airflow 3. We've also heard about Airflow using lower resources, and since we self-host, that's cool for us. And we are also excited about DAC versions. Next, we want to try the Edge executor, which maybe could help us simplify our connection of Airflow and Slurm. Although I was yesterday at Jen's talk, which was really good. And maybe we won't be able to use it yet, since we would really need to be able to run triggers inside the Edge executor, which is something it's currently not possible, and maybe it won't be possible at any time in the future. And finally, we want to implement assets everywhere. Wherever we have assets, we like it. We believe they are superior to external task sensors, which sometimes randomly fail. So we want to migrate to that. But we need to find a way to solve the problem of unscheduled DACs. So if the parent DAC fails for some reason, then the child DAC that is linked by the asset doesn't get scheduled, so you don't get a notification of, hey, this DAC hasn't run. So we want to investigate on what we could do in order to solve this problem. So that's it for my part.